Okay. Hi, everybody. In this lecture and in the coming two lectures, I shall illustrate to you a number of examples showing how we can build a control system model and how we can analyze its performance by using its time response to a unit step input, and also we shall find the body diagrams and compare between the results. We begin our study with the first order dynamic model. We shall represent the dynamic model by using a transfer function model, and we shall convert this transfer function model to a state space one also. Here is the icon which represents a first order dynamic element. The first input represents the static gain. I have given it number 1. The value is 1. And as a first order element, it has only one time constant, one root. I have given here the value, as you see, of this input, which represents the time constant 0.3. To find it, you have to right-click on the block diagram and move to Control and Simulation to Design Control, and then you move to Model Construction. In Model Construction palette, you will find here Control Design Construct First Order Model VI. You click it and put it on the block diagram as you see here, and then you continue your work with it. Another way to know if you have it on the block diagram, for example, in an example, and you do not know where it is, to which palette includes this icon, you right-click it and go to the help, click the help, and then you will see here the Owing palette. The Owing palette here is a model, which is the model construction VIs. You can directly here double-click it also, and you will have a number of VIs which belong to this palette. One of them will be the Control Design Construct First Order Model. You click it, and you can see how it looks like. You can add it directly to the block diagram also from there. So you have two ways to work with it. So now we have the icon of the first order element, and with a gain, static gain equal to 1, and a time constant equal to 3. Here we have a terminal which can create the model itself. as an indicator. So you double click it and see how it looks like. It has a numerator, 1, as we suggested. It has a denominator with a free term 1 and the other term with a factor dot 0.3. This numerator and denominator could be plotted as a formula or equation, and this will look like as shown here. 1 is the numerator, the free term is 1 here, and the first order element 0.3. How we created it, it is not difficult. I go to the control design and simulation and select this function here. Unit step response VI. No, this is not the one which I will work with. This one I will work with it to draw it. So I go there and select draw the transfer function equation. You go here, control and simulation, control design, and here we shall see how to draw the equation. At the construct model construction, here control design draw transfer function. We have 3 icons, one of them specifically for transfer function model, the other one for state space model, if you want to draw the state space model, and the third one also, which is the control design draw zero pole gain model. Control design has the ability to create 3 different types of the models. Mostly we shall work with the state space, then with the transfer function. We will not go and work with the control draw zero pole gain model because there is no need for that. It doesn't give any information specific, or it doesn't add any new information to the information which we can get by the transfer function. So we go there and click this icon and put it on the block diagram. You see this hand here, which with a pen, which means that you are going to draw something. The input here is the cluster, as you see, which represents the transfer function model. And at the output, you create as an indicator this equation. This equation which I have shown you just now. So the information which is here practically the same which is here, except that in this view you have it as a fraction with a numerator and denominator. Here the numerator and denominator are splitted separately within the cluster. Okay, so we have created the dynamic model. We have plotted the equation which represents this model. Now, if we want to have an idea about its performance, time performance, the response to a unit step, we import the control design step response VI. Again, we go to the control and simulation, control design, time responses, and here, control design step response VI. Okay, so now we know how to get any of them. Now we have this VI. We connect the model to the input directly, and at the output as an indicator, we shall also have step response graph. If we double click it and see how it looks like, here is the graph which represents the response of the system for a unit step. As you see, it is an exponential function, begins from 0. It has an initial 0, as we use Laplace transforms here. It has an initial 0, and as you see, it is a time, it is limited by time, so this is an indication that this system is stable. It doesn't increase forever, and it comes to a steady state about at this time here, at this moment of time, which is 1.5 seconds. 1.5 seconds is, as you see, the time required to rise from 0 up to the steady state. The time function or the time constant, usually approximately, it is about 3 to 5 times of the time which is required to settle at a steady state is equal about 3 values to 5 values of the time constant. The time constant is, you remember, dot 3. So dot 3 multiplied by 5, it will give you 1.5. So the time from here to here is exactly about 5 times the time constant. Now we shall also convert the transfer function model to a state space model. There is a specific icon in the control design where you convert models, model conversion. You can carry out many different jobs here. One of them I shall convert from transfer function to state space. Convert here, convert continuous to discrete. Here, convert discrete to discrete. Convert discrete to continuous VI. As you see here, convert to transfer function, and the first one here, convert to state space. So I have to click here and put it on the block diagram and carry out or connect the necessary inputs and get as the output a state space model. Here it is. So I cancel this node now. Now I have the input, which is the transfer function model, fed to the conversion model, which converts the input from transfer function mode to a state space mode. Now here at the output, I can create an indicator which shows the model of state space 1. This is the state, now a state space model. If I double click it and go there, it looks, sorry, here, it looks like, as you see, a cluster. It is a cluster. And now here are the different matrices A, B, C, D, which are inputs to the state space model. As you see here, this matrix has a coefficient minus 3.33. The C matrix have the same value, but it is positive. The B has a value of 1. We have only one input. And D is equal to 0 because there is no through input. There is no connection direct between the input and the output. So this is the representation of the state space model. This state space model is continuous and not discrete. Why? Because, as you see, the sampling time is given as 0. If I want to have it as a discrete one, so I have to go backwards here, and in this converter, I have to show exactly here the sampling time. It is not shown. Why? Let us see it exactly. Go to help, click show context help, and now if I put my hand here, yes, this converts. It doesn't have a time. It doesn't convert directly to discrete. I have then to convert the continuous to discrete at first. This continuous function must be converted to discrete one, and then the discrete one there, I can fix the sampling time. I shall show you just now. So now we are here. This is our transfer function fed to the converting palette, which converts the continuous transfer function to a continuous state space one. And we have seen the main matrices of this state space model. Okay, what we have also what I am doing. Okay. Now I have the state space model. The state space model, I can use a specific palette, VI, or a palette also, to get data from the model, to go and see what I have inside this model. This is the control design, get data from model. Here it is. This is the control simulation, control design. Here is the model information in general. And from this, I can go and control design, get delays, for example, control design, get data from model. This one which I have used. Here it is. This is specific for the state space, as you see. If you want to work with transfer function and see details, you can do that, but you have to change to transfer function, or you can work with it directly here. Here is the output to a transfer function. I can go to the control and simulation, control design, model information, get data from model. This is Now it is state space. I change it to transfer function. Now it is transfer function. I connect the output as a transfer function. And now I get the output which I want. Here I can get the numerator, the denominator, the delay if there is a pure delay or a transportation delay. Now let us, for example, create an indicator for the numerator and create an indicator for the denominator. Well, as you see, now if I go to the front panel, here they are. This is the numerator. This is the denominator. Now if I run, I shall get the values as they are here. This is 1, which is the numerator, and this is the coefficients 1 and .3, which are here as denominator. So we can do as we like. We work with very flexibility with this really control design tool. Another interesting thing, as you see here, I have extracted from the control design get data from the model. I have extracted matrix A, for example, only to see what it is. If you don't see what it is, here is matrix A. You will find that it is two-dimensional, and the values are there is minus 3.33, which are here. Here it is the same, two-dimensional with this value inside. So it works. You have no problem. One interesting thing also, I wanted to find the eigenvalues or vectors of this matrix, matrix A. I want to get the eigenvalues for this matrix. This is necessary for work also. These eigenvalues will equal to the roots of the transfer function. So let us find both. To get the eigenvalues, you go to mathematics palette, to linear algebra, and then to eigenvalues and vectors VI. I put it on the block diagram. Here it is. It is VI, is this VI again. I connect the input to the matrix. I am interested with matrix A, so I connect matrix A with this VI and selected the output as eigenvalues. Here they are. It is a complex value. Here only. No, it is not complex. It is one value. Yes, it is a real value with an imaginary equal to 0. It is still real. Minus 3.333. This value, which is here eigenvalue, one eigenvalue, because I have only one variable, one root to the transfer function. Now this value could be found also by using a polynomial equation in the mathematics palette. Here, this is the polynomial root VI. If you go to the mathematics, to the polynomials, here it is polynomial roots. You wire to the input here the polynomial, which includes the coefficients of the denominator of the transfer function, and then we will get here the roots. If you look at the roots, you will find that the roots is equal to the eigenvalues. Here also we have only one root, as we have one eigenvalue. Okay, suppose we want to find the roots on the block diagram, on the X or complex plane, on the complex plane. I can use for that purpose this VI. This is called the control design pole zero map VI. If I go here, control and simulation, control here, this is the control design pole zero map VI. It is this VI. Now this VI is connected to the transfer function. Yes. And at the output, I have got now an indicator, which is represented here. If I run the program, as you see, this is the poles shown in red crosses. This is the cross. Here is the -3, -3.2, -3.3. Here it is, in this area will be our root. Here it is shown. So you can find it positioned on the complex plane, and this is always also sometimes necessary to work with. Of course, you can do the same for the transfer for the state space. If I convert this to a state space model, now this doesn't work. Well, let us keep it and create a new one. Now we create a new, I drag it and I have a new VI. I connect now this VI to the state space from here. Why it doesn't, oh, sorry, I have to connect it to a state space. Now it works. And at the output here, I can get the information which I want. What are the poles? What are the zeros? And here, what I can get also, pole zero map. Let us see first of all the pole. The values here are indicators as values. So the zeros is equal to 1, if you remember. Okay, I create an indicator. This will show the 1 value. This is another indicator. Will show the 0.3, and this is the map, which is okay. I can create it also as an indicator. Okay, so now if I go to see where is zeros, poles, and pole zero map. This is the where is our indicators. I didn't see them here. Let us try to click and see them again. Okay. Where they are. Okay, let us try first to run the program and to see how they are shown here. Here it is exactly, as you see, minus 3.333 as it is here, the same values. The interesting thing, I doesn't see. Okay. I doesn't see the indicators where they are hidden. Maybe behind my face here. Yes, here they are. Here are the zeros. And here are the poles. Now, if I run the program, I have run it already. So there is no zeros. This is not a zero. This is a constant, static constant value. This the zero, there is no zeros. And the poles, we have only one pole, which is shown here, minus 3.33. So everything is working perfect. It is clear, but this is not really an adequate position for them. Let me position them for you here. Okay, now let us go back and see if there is another things. Ah, yes, I didn't illustrate for you the performance of the first order element in the frequency domain. So here we use the body diagrams. This is control design body VR. Body, you go to the control and simulation. Here is the control. Here is the frequency. And this is the main palette. Here the sub palette. From here, you can select the one you want. I have selected control design body VI, which is here. As you see, you need to connect the input, which is the state space here. No, it is not here. I didn't connect to the state space. I connected to the transfer function. So this could be yes. This is dedicated for the state space. If you want the transfer function, let me go back. Control and design, control design, frequency response. This is the diagram of interest. It seems that it works automatically. Let us try to connect with the transfer function directly. Does it connect? Yes, it automatically works. So, okay, suppose you want to see the frequency with the state space. So let us see, this is a state space here. And let's try to connect. Okay, so there is no problem. It automatically connects the transfer function to transfer function or to the state space, no problem. Now, the input in this case is the transfer function. The output, as you see here, the magnitude of the frequency response and how it varies by frequency, and the phase shift between the input and the output as a function of the frequency. If you go there, here it is. This is the upper function, which is the amplitude frequency characteristic. As you see, it is practically here constant. It doesn't change until you come to the knee position, and then it will drop down with a rate of 20 decibels by decade as for any first-order system. The slope of this line here, 20 decibels per decade in negative. This portion is usually called the knee portion of the amplitude frequency characteristic. This characteristic is exactly the same as any characteristic of a first-order filter. As you see, the deterioration and noise appears after the knee part from here at this frequency about 10 hertz, and then now the value begins to decrease until it comes to 0 and less than 0. The frequency or phase frequency change is as you see here, and the maximum phase shift is about 90. It should be a little bit less than 90. This is characteristic value for first order element. The first order element cannot have a phase lag more than 90 degrees. So this system, as you see in general, is considered stable. As you see, the response by time is limited and the phase shift is less than 180 degrees. So the element here, or the dynamic element, is stable and works fine. Okay, so let us go back and see what we have done here. In this example, I have constructed a first order element as a transfer function mode. I found the time response of a unit step applied to the input of this function. I have drawn the equation which represents the denominator and numerator. Yes. Also, I have converted the transfer function to a state space model. We have examined the matrices of this state space model. We have extracted from the model matrix A only. Why? Because we needed this matrix to find the eigenvalues of it, as the eigenvalues of this matrix usually represent the roots of the equation of the denominator of the equation of the transfer function. We also found the complex plane map where the root is located, and we have found that there is no zeros for this function. Of course, there is no zeros because this example doesn't have zeros. It has only one static gain. But I can give a zero value. I can add and make it with 1 0 or 2 zeros as necessary. At the end, we have also examined the frequency response of the dynamic element, and we have found that this dynamic element is stable also because the phase shift is less than 180. And I think that's all. So the conclusion, I have demonstrated for you how we can construct a dynamic model by using control design, and how we can convert this dynamic model to another type, and how we can analyze it dynamically and see how it behaves by time. I think this is a basic approach to control design so that you can understand how you can manage and move through this different palettes and select the appropriate one for the appropriate purpose. Okay, so with this, we finish today's lecture. In the next lecture, we shall continue with a second order and third order dynamic models. Until then, wishing you the best and goodbye.